for the end of day one. We have a few speakers left before the end of your day cocktail reception sponsored by Nalco, which of course you are all invited to stay for and visit the exhibitors booths while you're there. Am I doing okay on those reminders? Okay, perfect. With that, we have our next distinguished speaker, who is Volker Rummenhol. I did all right on that. It must be our long ago common heritage, I suspect. So he is going to provide comments this afternoon on CFD modeling for SCR performance optimization. And it sounds like there'll be a case study at one particular unit. And as we have done on all of our panels, we'll have him present and then hopefully have time at the end for some questions. So I suspect that will be of a technical nature. So with that, the floor is yours. Thank you.
Thank you. Good afternoon, ladies and gentlemen. I hope everybody got some coffee. And I always enjoy giving presentations after the coffee breaks. So, before I start with this presentation, I would like to acknowledge the authors of the presentation, Scott Heidemann from Kansas City Power and Light, Diane Fisher from Black & Veatch, and my colleagues Reed Thomas and Del Pfaff. This presentation is about the LaCygne 1 SCR. It's on a 680 megawatt unit firing PRB coal. And KCPL had severe problems with catalyst plugging from ash fallout. FuelTech received a CFD and physical modeling contract to find out what the reasons were and after that find possible solutions to it. I will talk about a device called Graduated Straightening Grid, GSG, and I will show you shortly in detail what that is. However, this GSG provided in this existing SCR plant a uniform vertical non-recirculating flow, which really solved some problems. Towards the end of the presentation, I will talk about the improvements of this project. This project was in 2012 and was ended in November 2012. And last but not least, some lessons for the design of SCRs. In general terms, among all coals, the PRB coal is the least forgiving coal because of the ash properties. We can see here the baseline flow model. This is half of the SCR. The unit has two SCRs which are arranged in a mirror image. And we have here the inlet into the ductwork of the SCR. We have inlet dampers, ammonia injection grid. There are two sets of mixtures and a large particle ash screen. Then we have turning vanes into the horizontal duct, and in the horizontal duct are stiffeners, and then we turn into the catalyst. This was during the first year, Kansas City Power and Light saw the pressure drop of the SCR constantly climbing. They had to take the unit down and vacuum the ash, and this is one of the diagrams they made after 1 year. And after 1 year, the first layer was 45% plugged with ash. And you can see here, or cannot see, but there was a huge ash accumulation on the turning vanes. And this is how the reactor looked from the inside. There were ash piles which were like 4 or 5 feet high. And here you see the one result from the CFD for the baseline design. And you can see several things. You see an area of very high velocity and then areas of very low velocity. And those areas of low velocity are the areas where you find lots of fly ash. Then you see, in order to straighten out the flow, an egg crate was installed, and underneath the egg crate were massive support beams to hold it up. And I will get back to that later. Another problem were the in this area, the gusset plates for the trusses, they created really high flow. Oops. And here you see the flow vectors, and they really show the biggest problem that this design had. You see here recirculating flow, and whenever you see recirculating flow, you can bank on that underneath that you will have ash fallout. So this is a big area, and you can see here that the flow is not parallel to the catalyst is at the inner corner, despite the egg crate on top of it. You can see this here as well. In other areas where the velocity is better, you can see the egg crate does its job, and you have parallel flow into the catalyst. So this shows us what happened, and this goes very well with the CFD we saw before. Those were the dust accumulations on the turning vanes. And before this project was started, Kansas City Power and Light tried with simple measures to help the situation and cut off horizontal parts of the turning vanes. However, it turned out that that didn't solve the problem at all. And you can see you have the on the first layer, the dust fallout from the turning vanes and from the rotating, the recirculating flow. This fallout, since there is also no flow on the lower areas, it was over time went through to the lower areas. Then we see here the beams that support the catalyst layers, and those massive beams also in that shadow were also dust accumulations. So now I want to show you the GSG, what we put in here. And you see we have now very parallel flow into the catalyst. We still have some small areas where we have angled flow. This was not yet the final solution. We made a few minor changes to it, but you can also see here that was not yet the solution we wanted to go with. And the GSG, what it is just in the diagonal of the reactor hood, small blades which are 2 to 3 feet high and 1 to 2 feet spaced, depending on the size of the unit. And this is the final solution. In total, we did 7 runs. We went back to run number 5, to which we chose. In order to really get the best possible result, we added 4 sections of 4 sections of perforated plates. They all had a different opening, and we chose them depending on the flow results without perforated plates. And this is now the final result. And since this is a retrofit of flow devices, you can't get to 100% where you really want to get to. And we were left with smaller, with areas of low velocities underneath some of the beams. We also had in the back, still a little bit area of velocity that we would like to see slightly lower, but since there was so much existing steel structure in the flue gas duct, this was the final result. What we also did, and I wanted to point that out, the other thing is we took this egg crate out of the reactor. And with taking the egg crate out, we also had to take out structural steel that supported the reactor. And you will see later we had to add external structural steel. This is how the project began. What we wanted to do is achieve an absolute velocity deviation of 15% for 100% of all measured points. The baseline had only 58% in it, and our final result had 91%. So we didn't quite achieve the our goal of 100%, and the reasons were those areas that I showed you in red, which we couldn't get away. But we were 99% with less than 30%. And there is always a discussion whether velocity distributions, whether you should take absolute values or statistical values like the RMS. The original RMS was 17.5%, and as a rule of thumb you can say if you double the RMS, that gives you the values in absolute. So that would be plus minus 35%. But you see, it was a major improvement. And you can see now, this was how it looked before. And this was after 4 months of operation. And when the unit, the SCR originally started out, after 4 months, it already looked like this. So the reactor's back in operation since November 2012 and has been inspected several times, and it's still clean as on the right side. Now I want to show you a little bit, a few pictures of the construction. The construction was very difficult because the SCR is high up in the air. Everything is enclosed. In the area where we need to work were only manholes. But this is the demolition of the turning vanes. This is the demolition of the egg crate, and you can see we also took out the steel structure that was carrying the egg crate. And therefore, you can see we also took other internal trusses out, and therefore, externally, it had to be stiffened. The reactor had to be stiffened. You can see here the crane, and here you can see what we did during the construction phase. We had to cut a hole in each of the reactors, and all the material came in through these holes, which were then closed later. And this is the GSG. You can see here the blades. The catalyst would sit down below here. And you can see the perforated plate sitting on top of the GSG. Here is the construction of the GSG panels. The GSG is hung up from the top, and the perforated plate is on top of it. You can see another thing we did here. These were dust accumulations on the lower layers below those trusses, and where we have the seals. And what we did, in order to get this clean is we put on the trusses a hood on top so that it really couldn't accumulate anymore. And these are the results, again, after 4 months with using those hoods on the seals. So the benefits the client, Kansas City Power and Light, has from this is reduced catalyst replacement. Before, they had to replace portions of the catalyst almost annually because they were so plugged. Reduced fly ash vacuuming. They had to several times a year bring the unit down and vacuum it. The pressure drop is now stable, and the fan power cost is before the unit had to be derated at times. And on top of this, if you are in a PRB unit and have significant ammonia slip, you won't have problems with the air heater or with the fly ash because there's so much calcium in the PRB ash that ammonia cannot attach to it. It can attach only to unburned carbon. But where it all ends up is in the scrubber, in the wet scrubber. And if the ammonia concentration in the scrubber is too high, it starts foaming. So the realized cost, annual costs were $5 million. So the payback time for the whole cost here is about 13 months. A little of the key issues for the design of SCRs, especially on PRB units. It's incredibly important that you have uniform vertical flow into the catalyst without any recirculation. For the SCR, the design criteria should always be in absolute values. We are using, for the velocity, for the ammonia to NOx ratio, for everything, we use absolute values. The CFD and physical modeling is really the key for the performance of the SCR. I said now twice CFD and physical modeling. The physical model was not used for the design because the timing was too short to meet the planned outage of the client. So we did the CFD, and then the detailed design was done. And after that, the physical model was used to validate the CFD, but it was not used for the design. Fortunately, it really validated it. It's always an advantage if the flow modeler itself has experience with the design of SCR plants. And then we come to one issue that is controversially discussed very often. That's how many cells should be used in a CFD. We used here only in the reactor area 5 to 10 million cells, depending on what we wanted to model. The whole SCR has used up just under 50 million cells. And the more cells you take, the more precise it becomes. When I started this modeling business in 2004, we had the most expensive desktop that we could buy, and we could run just over 1 million cells, and it would take us 8 hours. Today, we are not using desktops anymore. We have servers. And we can run now 50, 60 million cells. And since, I would say, that in the last 4 years, the accuracy of the CFD, especially for velocity distribution, is much higher than in the physical modeling. Another important thing is in the CFD, we have modeled everything that was in the flue gas pass. In the physical model, you can't do it. It becomes too small. So we modeled everything that's in the real plant, 6 inches or larger, was modeled in the physical. What's really important is to have minimal structures, minimize the structures inside the SCR for trusses and so forth. It's also a reason that, especially on PRB, sonic horns are so much more effective than soot blowers, just because the soot blowers require so many internal structures. For the catalyst design, if we choose for PRB units a honeycomb, we use 8 millimeter or larger, and for the plate, 5.6 millimeters or larger. Another thing is the ash is, because of the calcium content, so hygroscopic that you should avoid every moisture. And many of the PRB units we design have an outage layup to keep the SCR above the water dew point. Very important during the operation to check on the horns. You can hear when a horn is not accurately working, so I suggest to walk the unit down once a day. LPA screen failures, and you can fortunately detect them pretty fast by putting a differential pressure measurement over the LPA screen. And very important is the layout of the screen. We found out that if you keep the velocity, the average velocity between 45 and 50 feet per second, and the maximum local velocity not over 70 feet per second, then those screens are self-cleaning, and you can use the cheapest material for that. Vacuum of the catalyst, if there is any ash on the catalyst, vacuum is important, and then a continuous inspection and monitoring program of the catalyst. Oops, that concludes my presentation, and I'll be happy to answer any questions you may have.
Great. Any questions from the audience?
Any questions?
Hi, I'm Donnie Klotz with MNC. Have you had much luck with the tunable diode lasers for monitoring ammonia continuously on the outlet of the SCRs?
On coal units, not.
No.
We have, Fuel Tech has developed its own technology for continuously monitoring ammonia.
Yeah, I know that ammonia slip remains a challenge to determine it and to know what you have real time, and
Yes.
ammonia is probably coming down the pike here pretty soon to be one of the parameters to be monitored continuously in water or flue gas or whatever. So just curious if that technology has improved much for ammonia.
Yeah, what Kevin,
Maybe just a comment, as Volker mentioned, we're using a tunable diode laser in a kind of fixed path length where we're extracting gas out of the rough because one of the issues with KCPL is technology seems to be working, but sometimes you have alignment issues that kind of prevent you from really being able to reliably depend upon that signal. So I think the technology has really become industrially hardened, if you will, and it's more probably about the alignment issues that can be somewhat difficult for the plants to deal with. So we're more or less taking the same monitor and using it in a different concept in terms of extracting the gas, running it through, and then we're in the middle of just finalizing. We've done some testing on it, and we've got a couple of commercial units out there we're in startup on right now. So, but I totally agree, ammonia monitoring, because that's not only on an SCR side, but on SNCR, you also have that issue as well, relative to monitoring performance and keeping away from air heater and bisulfate issues.
Any other questions?
Thank you.